Hello and welcome to the first tutorial in the T325 course, which is about power for digital media. The outline of this tutorial is as follows. It starts with an introduction about power for digital media. Then we're going to talk about the battery technologies, some characteristics of the battery, the main metrics that present these characteristics. Then we are going to talk about fuel cells, which consist one of the trends in the battery technology, and finally conclude with some discussion about the power from the environment and the energy harvesting. So power consumption is one of the main constraints in the design of electronic goods, and this is not an issue for the mobile devices, where we all know that the power consumption is one of the challenges, but even for mains power equipment, and you all know that when we buy these equipment, we find a kind of classification of these equipment into class A, B, C, etc. Based on their power consumption, and usually we select the high level classes A and B. So why this? Mainly this is related to the fact that the power consumed usually ends up as a heat, and this heating has two implications at the micro level and the macro level. At the micro level, when we think about that, overheating of electronic circuits damages the components of these circuits, and at the macro level, when the energy consumption has direct impact on the global warming, which is a worldwide issue. So one of the intuitive questions to ask is that, do these small electronic devices consume that much of energy? So these mobile phones or handheld devices. So if we have a look on some figures, so we can have a look at this pie chart that represents the United States residential electricity consumption, and we look that we see that around 31% of the consumption is related to devices that are considered as small electronics, such that TVs, set-top boxes, PCs and equipment, and all the handheld devices. In the United Kingdom, 23% of the average household electricity bill is for consumer electronics and computer products. And this, if we look at the trend, and you can see that the mains power equipment usually are decreasing the power consumption, while the small electronics usually are going toward the increase in their power consumption. And this is mainly because of the number of devices increasing in our daily life usage and the frequency of using these devices. And we all know how many times we are charging and recharging our mobile phone, as a small example of why we have this increase in the power consumption. So let's start talking about the battery technology. So as we all know, the batteries produce electricity from a chemical reaction. These are the classical batteries, and this reaction is called electrochemical reaction because we are generating electricity from the chemical reaction. So the image in the slide is related to one cell, when we can see there are three main components: the anode, the cathode, and the electrolyte. And usually, by definition, the anode is the part where the electrons flow out, the cathode where they flow in, and the electrolyte in which they are immersed. So in order to have, the battery usually consists of several cells connected together. So the chemical reaction in the battery depends upon the material used to make the anode, the cathode, and the electrolyte. And when we combine different types of chemicals, we will have different types of batteries. We all know about the alkaline batteries, the NiCd, nickel cadmium battery, the nickel metal hybrid battery, and the lithium ion batteries, which are commonly seen and used in the mobile phone. In addition, the chemistry and the details of the physical construction determines whether the battery can be recharged or not, and thus we have two categories of batteries. the primary battery, which is manufactured to be used once and then thrown away, and the secondary battery, which are the battery that can be rechargeable. An example of the primary battery are the alkaline battery, while and the lithium battery, and the lithium ion battery are an example of the secondary battery. So after looking at the general overview of the battery, we're going to go into some details and characteristics about the battery. The first characteristic we're going to look at is the voltage. And by definition, the voltage is the electric potential difference between 2 points. So usually in a battery, this is determined by the material used for the anode and cathode and the electrolyte. Usually, and we all know that if we need high voltage, we connect the battery in series, and thus the voltage will add together. The voltage is a characteristic for a battery that is not in use. So when we start using the battery and the current is drawn from this battery, the voltage will start dropping down. And if we have too much current that is drawn, the battery is discharging, and a certain time the voltage will reduce until reaching a minimum threshold. And after this threshold, in general, the battery is no longer usable. So talking about the current, we should know that the maximum current that is can be drawn from the battery depends on the load the load for this battery, or the external load for this battery, and on the internal load or internal resistance of the battery. Thus, you might have two batteries with the same voltage, and when they are connected to an external load, we might find the difference between the current drawn from each of these batteries. And this is mainly related to an internal characteristic of the battery, which is the internal resistance. So if we have two battery A and B, and both are, let's say, 1.5 volt, and they are two connected to the same external load, and we find that battery A is delivering a current that is higher than the current from the battery B drawn from the battery B, we can deduce that the internal resistance of battery A is smaller than the internal resistance of battery B. To model this, we can have a look. Each battery has an internal resistance, so it is characteristic by the voltage and the internal resistance. And when connected to an external resistance, or L, we can have the equation that the current is equal to the voltage over the sum of two resistance. Another characteristic for a battery is the energy. And usually it's important to differentiate between energy and power, which are loosely used in common speech. So the energy is a characteristic of a battery that is not in use. When we start using the battery, we will have the power that is dissipated and transferred from this battery. Thus, usually when you use the term power, this means that the battery is in use, while we can characterize a battery by an energy even though it is not being used. So by definition, the power is the rate at which the energy is being transferred. The energy is measured in joule as an SI unit, and the power is expressed in watt. So we might have other units that represent the energy, such as the watt hours, and there are direct relation to convert from one unit to another unit. So as I said before, the watt, the power is the rate at which the energy is being transferred. So the power expressed in watt, the energy is expressed in joule, and the relation is that 1 watt is equal 1 joule per 1 second. The formula that gives the power related to the voltage and the current is that the power is equal U times I, and we're going to look later on at the different formulas and equation to remember. Another characteristic of the battery is the capacity. And the capacity is expressed as the current drawn from the battery times the time and multiplied by the time in which the current is being drawn. So this is expressed in the unit of the capacity, which is the ampere hour, which shows the main two components that are multiplied to get the capacity. Also, it can be expressed in milliamp hour. So let's consider this example. If we have a battery with a capacity of 1 ampere hour, this means it can supply 1 ampere current for 1 hour, or let's say 2 ampere but for half an hour. So the capacity is what is stored in the battery. Depending on the current we're going to draw from this from the battery, we can have an idea about how much time it can last for. So let's have a look on the different formulas we had so far. So we have the power that's equal to the energy over time. We have the power that is equal to the voltage times the current. And we have the capacity that's equal to the current multiplied by the time. From these equations, we can deduce that the energy can be expressed by the voltage times the capacity. So, and you can have a look about the detail on how to move from this equation to this equation. All these formulas can be used to deduce one characteristic of the battery from other characteristic. So, looking at one practical example, and this is the back cover of the battery of a mobile phone, we can see that we can read the voltage, which is 3.8 volt. This is a lithium-ion battery. We have the 12.16 watt hour, and let's think a little bit. We have the watt that represents the power and the hour that represent the time. Go back one slide. If we multiply the power and the time, we're gonna get the energy. So this represents the energy stored in this battery. And having, let's say, the energy and the voltage, using this formula, we can get the capacity of this battery. And look, all these characteristics are independent from the consumption of the power. So these characteristics are for a battery that is not in use. When we start using the battery, we can then calculate the power when we have the current drawn from the battery, and having the capacity and a current drawn, we can get the time at which the battery can last for. So this is an example when we have the voltage and we have the capacity, and they ask us how long could it run if the load has a resistance of 30 ohm. So if you're gonna think, we have the capacity that gives us which is the current multiplies by the time, and we have the voltage, and we need to know how much time it can last for. So we have the current times time. We need the time, so we need to have C equal I times T. Knowing C, and to get T, we need to know I. How to get the current? We have the voltage and we have the resistance. By using the equations that says that the voltage is equal resistance times I, so I is equal the voltage over the resistance, we can get the current. And then when we have the capacity and we have the current, by dividing C over I, we get the time that the battery can run for. So this is another example. So we can see how to calculate the energy knowing the capacity and the voltage. So E equal U times C, and we can convert from watt hour into joule by converting the hour into seconds. Thus the answer will be in the SI unit, which is in joule. So we have different batteries of different sizes, different characteristics. How we can say which battery has better performance? In order to do this, we need to do some normalization of these characteristics. We cannot compare a battery that is 1 meter cube volume with a battery that is 4 centimeter cube volume. We cannot say which has better performance, since the sizes might differ. That's why we need some figures that allows us to compare different batteries from different sizes, and these figures are known as the figures of merit. So if I want to compare batteries of different weight, sizes, and capacity also, we're going to use these figures of merit, which are the following. Let's start with the volumetric energy density. And as its name indicates, the volumetric energy density is equal to the energy over the volume. The density is usually a ratio. This is the density of the energy related to the volume. This is why the equation is the volumetric energy density is equal to the energy over volume. Applying the SI units, the energy is in joule, the volume is in meter cube, the unit of the volumetric energy density is joule per meter cube. Another figure of merit is the gravimetric energy density, which is equal to the amount of energy stored per unit mass, and this is why this is the ratio of the energy over the mass. The energy again is in joule and the mass is in kilogram, so the gravimetric energy density is in joule per kilogram. This is the SI unit. However, other units can be used, such as the watt-hour per gram, watt-hour per kilogram, kilowatt-hour per kilogram, and the same for the volumetric energy density, when we can have joule per liter, joule per milliliter, so watt-hour per liter. All these units are valid. However, the SI units are the joule per meter cube for the volumetric energy density and joule per kilogram for the gravimetric energy density. So when the battery is now in use, so the power now can be calculated, and thus we have two new figures of merit, which are the volumetric power density and gravimetric power density. The volumetric power density is the ratio of the power over the volume, and the unit is thus watt per meter cube, and the gravimetric power density is in watt per kilogram in SI unit. And as we said before, for the volumetric energy density and gravimetric energy density, we can have other units such as the watt per centimeter cube, watt per liter, watt per milliliter, and again watt per gram, kilowatt per kilogram, etc. So let's consider this kind of activity. So this is a typical exercise to practice the calculation of the figures of merit. So we have the voltage, the capacity, weight, and volume. In order to calculate the volumetric energy density and gravimetric energy density, we need to calculate first the energy. So the energy, as we have seen before, is equal to capacity times voltage. And now, to get it in SI unit, we need to convert all units into SI. So let's say the milliampere hour is not an SI unit, since we have the milliampere while an SI unit is in ampere, and we have the hour. So the first thing to do is to convert the milliampere into ampere and the hour into seconds. So milliampere will be converted by multiplying times 10 to the power minus 3, and the hour will be converted into second by multiplying with 3600. Again, the weight should be converted into kilogram, so 24 gram is 24 times 10 to the power minus 3. The volume should be converted into meter cube, so by multiplying times 10 to the power minus 6, so it will be 8.4 times 10 to the power minus 6 meter cube. And the rest of the calculation you can do it using the previous formulas we have seen. So the same battery with the previous characteristic now deliver a current of 1 ampere. Now they asked us to calculate the volumetric power density and the gravimetric power density. Again, the key point is to calculate the power. When we have the current and the voltage, we can calculate the power, which is U times I. And now, having the power and using the previous characteristic we had for the volume and the weight, we can calculate now the volumetric power density and gravimetric power density. Pay attention that in this question they asked us to calculate in watt per liter and watt per kilogram. So this is why we converted the volume into liter. While if the question is about calculating these metric figures of merit in SI units, we should have used the watt per meter cube and watt per kilogram. So at the beginning of this lecture, we differentiated between two types of batteries: the rechargeable battery and a non-rechargeable battery. The rechargeable battery are the secondary battery, and non-rechargeable battery are the primary batteries. So in order to recharge a battery, we need to reverse the discharge reaction. So we have to do the reverse operation. And this cannot be done forever. And we know this practically, that rechargeable battery after a certain time will not be recharged efficiently, and a certain time they will not be recharged anymore. So they will lose their charge in a couple of seconds. So this is why we define what we call the recharge cycles, which is the limit or the number of times after which we cannot recharge the battery anymore or efficiently anymore. So the current will be drawn in the opposite direction of the discharge current in order to reverse the operation. And it's very important to note that the way we are charging or discharging will have a significant influence on how effectively it can be recharged, and thus on the number of the recharge cycle. So if we can respect a number of guidelines while charging a battery or discharging a battery, we can extend the lifetime of a battery. So talking about these aspects, for instance, we should not attempt to charge the battery too fast. This is why in many devices, when you have fast charging and slow charging, it's always recommended to use the slow charging for the good health of the battery. Another point is to stop charging the battery when it is fully charged. This is regarding the charging of the battery. While discharging, again, it's not healthy for the battery to discharge it too fast, like if there are a kind of short circuit, and this will lead to overheating the battery, and in extreme case will lead to the explosion of the battery. In order to control these aspects, we need to make sure that after a certain threshold the battery will stop charging, and this requires some control of the batteries. This intelligence is usually introduced in the smart battery, where we have a kind of microprocessor that controls the battery and thus will control the charging and discharging, and stop at a certain time if we have charging, or stop the discharging if there is a kind of short circuit. And this will protect the battery further, and it's from a safety point of measure considered as an added value to the use of battery, and this is what we call the smart battery. So to conclude about the battery characteristics, we have two important characteristics, which are the shelf life and self-discharge. As its name indicates, shelf life is the length of time a battery can be stored even if it is not being used. This characteristic is very important in the military application, where we might need to store the battery for a long time without using it, at a certain time going and starting to use it. So we need battery with long shelf life that allows us to use it when needed without losing the efficiency of the battery. Another characteristic is the self-discharge, which is the battery that loses the charge when not in use. And this is an important characteristic, that if we have a fully charged battery and then we keep it aside without using for a certain time, and then we're gonna need to use it again, so the amount of charge that is lost during this period is an important characteristic. For instance, as to have an idea about these numbers, the NIMH batteries lose up to 20 to 30% in a month, while the lithium-ion battery, which are commonly used in the mobile phone, lose up to 25% per month, and this is very important. Now let's have a look on the environmental issues related to batteries. So the primary batteries are in general very inefficient in the use of energy, mainly because we are putting a lot of energy to manufacture a battery that is much higher than the amount of energy that this battery will give us when we put it in equipment. So this problem is somehow solved with a secondary battery, where we can recharge the battery a number of times depending on the recharge cycles. However, we are still giving the battery more energy to recharge it than it will provide us. In addition, and it is clearly seen at the back of the batteries, rechargeable battery or secondary batteries, that the disposal of these batteries can damage the environment, and thus it should be disposed in a proper way. So now let's talk about, briefly talk about one aspect or one trend in the battery technology, which is the fuel cells. So by definition, a fuel cell is an electrochemical energy conversion device. Looking at the component of this type of battery, we are going to see that it produces electricity from an external quantities of fuel that we put on the anode side and oxidant on the cathode side, and in between we will have the electrolyte. So it have the same general structure of the classical batteries, but the difference is the type of material we are using. So the term fuel cells is related to the fact that these batteries consume reactant like cars consume fuel. So whenever we want to replenish the reactant in order to have more energy for the battery. So it consumes the reactant that is present at the anode side, and then when this reactant is consumed, we replenish the battery to use it again. So this type of battery was previously used in space rockets, but since 2007 or 2006 it has been introduced for use in portable devices. The interest is mainly because of the increasing demand and for power by digital devices, and the batteries are not capable of keeping up, and just for the fact that how much is it attractive to be able to revive a laptop by putting a cup of liquid fuel. So the aim of this research is to produce a small, cheap and safe, and we have a focus on the term safe, fuel cell for electronic devices. Now let's have a look on how to get power from the environment, which is also known as energy scavenging or energy harvesting. And a lot of examples such as the solar energy, wind energy, water energy, etc. The applications are many. Examples are the use of the energy scavenging for wireless sensor networks, where the node in these networks usually should have an energy source that is not, where we do not need to change the battery frequently. So if we look at where the energy comes from, we can see that most of the energy comes from fossil fuels, which is really a major problem, and this is why there is a huge push towards finding solution for this issue, and which can be done in two axes. The first is to find alternative to fossil fuels, and the second is to reduce the energy consumption, which is the responsibility of the ICT industry. So the European Union established a framework for setting of eco-design requirement for energy using product, which goes into the second axis. And the first axis, as we have seen before, is about finding the alternative of to the fossil fuels using the solar energy or wind energy or power energy or water energy.